So I'd like to start with three um, applied sounding questions. So the first is, can a data set be interpolated by a smooth function? So I've shown in the slide a very simplified picture in which Rn is represented by a horizontal axis and Rd is represented by a vertical axis, and we have some data points. And in the left-hand picture, it seems clear that the data can indeed be interpolated reasonably by a smooth function from Rn into Rd. Whereas in the second, in the picture on your right, the data cannot reasonably be so interpolated. Of course, there is, let's say, a C infinity function that passes through all the data points, but oh my God, its norms in any reasonable space of functions will be enormous. So, all right, so that's the first question. How can we decide whether a data set can be interpolated by a smooth function? Okay. Wow. And again, all right. All right. Now, if we decide that our data can be interpolated by a smooth function, then we should go ahead and interpolate it, as in the two pictures in this next slide. So interpolate data by a function that is as smooth as possible, whatever that means. So these questions right now are vague, and a substantial part of the talk will be devoted to pinning down their exact meaning. Okay. And the third question is to detect and remove outliers. So perhaps in an actual data set, perhaps most of the data points can be nicely fitted to a smooth function, but a few of them are just way off. And we want to detect which data points could be rejected as outliers so that the remaining points can be well interpolated. Okay, so those are the three questions. All right, let's now we want to perform these tasks with a computer. This is, of course, a theory talk, so there is a mathematical idealization of a computer, a Turing machine or something. We want algorithms that perform these tasks with no assumptions about the geometry of the data. That is, the algorithms should always work. And we also want efficient algorithms. We don't want to wait until the end of the universe to get an answer. We want to make minimal use of computer resources. Okay. So for simplicity, this talk is going to talk almost entirely about functions from Rn into R1 that fit a data set exactly. But in full generality, the results pertain to functions from Rn into Rd that fit a data set to a specified tolerance, and we'll briefly touch on that at the end if there's time. Speaking of which, when should I end? Should the talk take
I
about
think it ends at about 15 minutes.
50 minutes?
So,
Okay.
Yeah.
Okay.
So like 252 something.
Okay. Okay. All right. Now, all right. All right. We want smooth functions and we want as smooth as possible. So what does that mean? Well, let's say X is going to be our favorite Banach space of continuous functions from Rn to the reals. And the norm of a function in X is going to be written as shown on the slide with a subscript X. In this talk, I'm just going to consider two function spaces. I think there's one other that I've thought about, but let's stick to these two. The first one is simply Cm of Rn. So that's for this talk, that'll be the space of all functions which together with their derivatives up to order m are continuous and bounded. So for example, e to the x is not a Cm function because it's not bounded. So one Banach space is Cm, and you see the Cm norm written on the slide. On the other hand, we could look at a Sobolev space. So that's the space of all functions which, together with their derivatives up to order m, belong to LP for some specified p. And I've written the Sobolev norm on the slide. Now, as it says on the slide, X, our Banach space, should consist of continuous functions because we're going to try to fit finite data sets. So we had better make sense out of the value of a function at an individual point. And if our function isn't continuous, it's not clear how to define it at an individual point. So X should always consist of continuous functions. And so for the Sobolev space, what that means is that the index P should be strictly greater than n over m. N is the number of dimensions of the Euclidean space, and m is the number of derivatives we assume we've got. In this talk, I'm going to assume that P is greater than n rather than merely P greater than n over m. And so that means that X actually consists of functions with m-1 continuous derivatives. The mth derivatives belong to LP but are not continuous, so you can't talk about them at an individual point, but derivatives of order up to m-1 make sense at individual points, provided P is greater than n. You might wonder by the end of the talk, what's going to happen if P is bigger than n over m so that the question makes sense, but not bigger than n, which means that the results I'll tell you don't apply. And the answer is I haven't the faintest idea. And I've been thinking about it together with a few friends, and we're very far from the answer. Okay, so let's try to pose the interpolation problem a little more precisely. So we fix our function space X, and let's say E is a finite subset of Rn, and capital N is always going to denote the number of points of E. I'm going to think that little n is small. Maybe where E is contained in 3 dimensions or something like that. So of course, many applied problems involve high dimensional spaces. And although RD, the target space in which f of x takes its values, might be high dimensional, in this talk, the n is going to be small. Okay, so we're given our finite set E, and we're given a function f from E to the reals. And our data consist of the function f defined on the set E. What we want to do in order to interpolate the data is to find a function capital F in this Banach space X, which does 2 things. First of all, it agrees with little f, the given function on the set E. And secondly, its norm in the space X is as small as it can be, subject to the constraint that it agrees with little f on E. Well, maybe it doesn't have to be as small as possible. It's enough for it to be almost as small as possible. And we'll see what we mean by almost as small as possible. So let's define the norm of little f in the trace space X of E to be simply the inf of the X norms of all the functions capital F that agree with little f on E. Notice it's an inf, not necessarily a minimum. In particular, if X is Cm of Rn, there are very simple examples in which there is no minimum. The inf is not attained. Okay, so that if that and other considerations lead to the idea of an A optimal interpolant, which I'm going to define on the slide. So A is going to be some constant bigger than or equal to 1, and an A optimal interpolant for our data set Fe is a function capital F in the Banach space X that agrees with little f on E and has norm in the space X as small as possible up to a factor of A, as shown on the slide. So if A is 1, that means that in fact the norm of capital F is the least possible. In particular, there's a minimum. So in fact, in simple examples, you can't take A to be 1. But for practical purposes, ultimately this is supposed to be practical. We'll see whether we may or may not see whether it ever is. But if A is not so big, this is useful. Okay, so all right, now I can pose the interpolation problem with a little bit more precision. Okay, so we're going to fix X, our space of functions on Rn. We're given a finite set E and a function f defined on E, and we want to compute the order of magnitude of the trace norm. And we also want to compute an A optimal interpolant for a not so big A. And we want to do this by efficient algorithms that work for completely arbitrary interpolation problems, that is, completely arbitrary capital E and F, E finite. So that covers 2 out of the 3 problems. So far, I've simply dropped all mention of outliers, but we'll come back to outliers later. The problems, the way I've stated them, are still not precise, right? What does it mean to compute the order of magnitude of something? And what does a not so big A mean? So let's sharpen the question further. So I want to introduce the notion of controlled constants. So a controlled constant is a positive number determined entirely by the choice of the function space x and independent of the particular interpolation problem or any other data. I'm going to denote controlled constants by the letter C, some variant of the letter C, lowercase, uppercase, C prime, C asterisk, whatever. But symbols like that might denote different controlled constants in different places. So that's a controlled constant. Okay. And now I can give a more precise version of our problems. We fix our function space x, given a finite set E in Euclidean space, and given a function little f defined on E, we want to compute a number that I'm going to call the triple norm of f with the property that it differs from the trace norm um, of norm of f sub x of E. It differs by multiplicative constants, both of which are controlled. Okay, that's what I mean by computing the order of magnitude of the trace norm. So if the trace norm is enormous, then that means that we really cannot interpolate it by smooth functions. And if the trace norm is small or medium-sized, that means that we can go ahead and interpolate it by smooth functions. So if we compute the order of magnitude in the sense of this slide, it means that we may not know the trace norm precisely, but at least we know whether it's real big or not so big. And so we will know whether our data can reasonably be interpolated by a smooth function. If our data can be interpolated by a smooth function, we would like to compute one. And so the bottom of the slide poses the challenge to compute a C-optimal interpolant F, capital F, for a given data set where capital C is one of these controlled constants. So our interpolant may not be the very best, but it's the best up to some constant multiple. Okay, so that's the problem. That's still not precise because I haven't said what it means to compute. We're computing a number and computing a function. So I'm imagining that we're using a computer. The computer, let's say, has standard von Neumann architecture. And let's say for this talk, a computer is capable of storing in one memory cell an exact real number without round-off error. And it's capable of performing arithmetic operations perfectly without round-off error. Given more time and perhaps more interest on your part, I could discuss versions of these problems in which you assume finite precision arithmetic, but let's not do that. So that's what it means to compute. Well, so computing a number means that you enter the data and the computer executes an algorithm and spits out the triple norm of f, but it's not yet clear what it means to compute a function, because of course a function involves an infinite amount of data, and the computer ever holds a finite amount of data. So here's what I mean by computing a function, okay? We're going to enter the data into the computer. The computer will then perform one-time work, after which it signals, okay, I'm done with the one-time work. You can go ahead and ask queries, and the computer will answer our queries. A query consists of a point of Rn, and in response to a query X, the computer executes a query algorithm and outputs the value of the function at capital F at X, together with as many derivatives as we're allowed to have. So if we're working with Cm, our functions have m continuous derivatives, and we demand that our query algorithm will output all the derivatives of f up to order m. If our function space instead is the Sobolev space WMP, then we know that derivatives up to order m-1 are continuous and take values at individual points, but the mth derivatives, not so much. And therefore, our query algorithm is supposed to output the value of f together with its derivatives up to order m-1. So by now, there is a precise statement of two of the three problems that I mentioned at the beginning, namely decide whether a data set can reasonably be interpolated by smooth functions, and if so, compute a smooth interpolant of the data. I said that I want only algorithms that always work, and we'll see in a couple of slides that that makes the problem much harder. There are evil cases in which one has to be clever. Um, uh, but also I want the algorithms to make minimal use of computer resources. And so in the next slide, I'm going to mention what those resources are. So there are three. There's the one-time work, the query work, and the storage. So the one-time work is simply the number of computer operations used to perform the one-time work in computing a function. Um, and so a computer operation means, for example, adding two numbers together or fetching a number from a given memory location. Okay, so that's the one-time work. Similarly, the query work is the number of computer operations used to answer a query. And finally, the storage is the number of real numbers that can be held in the RAM. Um, now, presumably we're going to do the one-time work only once, hence the name, but we're going to address lots of queries. So it's much more important for the query work to be small than there is for the one-time work to be small. It would be, I mean, it would be nice also for the storage to be as small as possible. One is used to the idea of trade-offs, but by sheer good luck, the algorithms that I'm going to describe will optimize all three computer resources simultaneously. Okay, so those are that for now is the discussion of computer resources. Now I want to come back to the question of algorithms that work always. So given any finite set E and any function on E with, if we make no assumptions on the geometry of E or the behavior of F, we still want the algorithms to work. And so in the next few slides, I'd like to explain how trouble might arise. Let me check how long I've been talking. Okay. Okay. So in the first example, our set E is the set of dots in the picture that you see on the slide. So I haven't at all told you what the function f is. I'm not going to. We're just looking at the set E on which the function f is defined. Notice that all but two of the points lie on a horizontal line. And so those two exceptional points are called A and B. Now, suppose I give you a function defined on this set, and I ask you to interpolate it with, let's say, a C4 function. Okay. Well, look at the point X and ask, what is the gradient in the vertical direction of our interpolant at the point X? Now, all the information for that query has to reference the points A and B. Any algorithm that doesn't look at the points A and B has absolutely no information about vertical gradients, right? If you know a function, if you have beautiful, exquisite knowledge of your function restricted to the x-axis, you know nothing about its y derivative. On the other hand, if you look at A and the two neighboring points, they form something like an equilateral triangle, and you can interpolate that reasonably and decide what the vertical gradient is there. And similarly, if you look at the point B and its two neighbors, you can figure out the vertical gradient there. And now the point X is not so far away from the points A and B, and so you could maybe make a linear interpolant of the vertical gradient as a function on the x-axis, and it will soon enough lose accuracy, but at the point X, it's pretty good. That's actually the only information you've got, so you might as well use it. Now, what lesson does this give? Well, A and B may not be among the 10,000 closest points to the point X. And therefore, if you are using any interpolation algorithm that decides what to do about X by referring to the 10,000 points closest to X, it has absolutely no chance of being right. So we had better look. If this situation happens, we'd better detect it quickly and respond to it. Example 2 looks more general, but it's basically the same. So imagine E is the set of dots on this alpha-shaped thing, which is supposed to be the set where some polynomial is 0. Let's say the polynomial is of degree 3, and we're interested in C4 functions. Okay. Now, if you don't look at the points A and B, which are the only ones that do not lie on the 0 set of the polynomial P, if you don't look at those, then you cannot tell the difference between the function capital F and the function capital F plus P, or capital F plus 1000P. And so unless you are looking at the points A and B, you will be in deep trouble. Now, of course, I have drawn this curve, but in the statement of the problem, nobody is going to give you the curve. You will simply see the set of red dots. And so if you see that set of red dots, you will have to detect the presence of the curve and respond to it very quickly. That's still not the full difficulty of the problem. To get an idea of the full difficulty of the problem, imagine that E sitting in R3 in Euclidean space is the set of dots shown below. And what's happening here is that all but a few of the dots lie on this two-dimensional surface sigma, which is the 0 set of some polynomial P. Looks to me as if P is maybe quadratic. And on the other hand, of the dots that lie on the surface sigma, all but a couple of them lie on the curve gamma, where not only P, but also Q is 0. Q is some low degree polynomial. And so just as in examples 1 and 2, in order to respond to this situation, if you're given only the green dots and neither the curve nor the surface, you would better find the curve and the surface real fast and respond. So those are some of those are the main issues that confront any attempt to build an interpolation algorithm that always works. Okay, so now let me describe what algorithms we can produce, and I will say a little bit about the ideas behind one of them. Okay, for when X is Cm of Rn, when that's our function space, I'll be describing joint work with Boas-Klartag from about the year 2008. I forget exactly when, roughly 2008. And when our Banach space is a Sobolev space and P is greater than the dimension n, this is a joint work with Aryeh Israel and Garving, aka Kevin Lully. Okay. So what can we do? Well, fix X as above, one of the two. Given a data set E comma little f with capital N data points, we're going to compute a C-optimal interpolant using one-time work that grows like, well, as shown on the slide, one-time work at most Cn log n, query work at most C log n, and storage at most Cn. Now, very likely, these are theoretically optimal. For example, the one-time work, it would be nice to read the problem before answering it. Presumably, the students graduating today have learned that in taking their exams. And so, well, if there are n points, it takes n operations to read the data. And here this algorithm works in O of n log n operations. How about the query work? Well, to read a query presumably takes work 1. To answer a query also takes work 1. So I guess the query work is at least 2, and here it's at most logarithmic. How about the storage? You had better store the problem, because if somebody asks you what your interpolant is doing at a point of E, you had better remember what the given function little f is at E. So you'd better store the function little f. And if you do that, the storage is n. And so the storage is within a constant factor of optimal. So theoretically, this is optimal. And it's so it always works, and it makes minimal use of computer resources. And isn't this wonderful? And isn't it useful? And the unfortunate answer is no, this is not at all useful, because whereas some of the other constants C are somewhat reasonable, the constant C in the statement we compute a C optimal interpolant F is ridiculously large. And so the interpolants produced by this algorithm are not of practical use. There is one particular lemma in which forces C to grow absurdly fast. And if if that one lemma could be proven much more efficiently, it is conceivable that this stuff it would actually be a practical use. I have no idea whether that can be done or not. Okay, and oh, by the way, the interpolant that we produce depends linearly on little f for fixed e, and so that means that answers the theoretical question: is there a linear interpolation operator? Yes, there is. Um, Now, that's the construction of interpolants. How about the calculation of the order of magnitude of the trace norm? And the answer is that that can also be done efficiently. That is, we can compute this triple norm of f, which differs from the trace norm by at most a controlled constant factor. And in order to do that, we use at most O of n log n computer operations and at most O and O of n storage. And again, that's very likely optimal for very simple reasons. Okay. All right. And so here again on the slide is, can these algorithms ever be made practical? And in order to do that, we have to reduce these controlled constants C, especially the constant C in the statement that that the interpolant is C optimal. Can that ever be done? Can we ever do it? Maybe, maybe not. Okay, that's the status of that. Now let me come back to outliers. So let me try to state the problem precisely. So let's just look at the space Cm of Rn. So I don't know anything about this problem for Sobolev spaces. So let's say we're working in Cm of Rn. We're given our usual data set with capital N points, and we're given some number z, which is small compared to n, but may be pretty big. What we want to do is to find a set S, a subset of E, those are going to be the outliers, okay, containing at most Z points in such a way that if you take those points away from E, then the trace norm of the remaining problem is as small as possible. Here, I guess I've been sloppy. I should have said the trace norm of F restricted to E minus S, and then the norm of that in the space X of E minus S. But I think it's clear what I meant. Okay, so that's the problem. I give you a data set EF. I think it contains some outliers. I give you a number Z, and I tell you that you get to remove Z data points from the problem. Please pick those data points so that the remaining part of the data set can be interpolated with as small a norm as possible. That's a real hard problem, so I'm going to solve an easier problem. So let's say that a subset S is C optimal if there does not exist a competing set S prime contained in E such that S prime contains far fewer elements than S, so that the number of elements of S prime is less than C times the number of elements of S. But at the same time, by removing the set S prime, we do a lot better than by removing the set S. And so the two inequalities on the slide are what it means for the set S to be C optimal. So let's say, if I can put it this way, let's say we're competing with God. God picks the perfect S immediately, and so his S has fewer than Z points and has the least possible trace norm once you've removed it. We are unable to do that, but we win an unfair contest against God in which we can remove 10 times as many points as God, and we say that we've won if the trace norm of our entry is no bigger than 10 times the trace norm of God's entry. Okay, so that's a C-optimal interpolant, and what we're going to try to do is produce C-optimal interpolants for a controlled constant C. Okay, and the theorem is the following. Given a data set, we remember with capital N points, we can enumerate the data set, we can order it, we can say it's x1, x2, and so on, xn, in such a way that for any z up to n, the set S sub z consisting of the first z entries is C optimal. So morally, x1 is the very worst outlier, x2 is the next worst outlier, and so on. And so if you want to remove z outliers, you should remove the first z of those x's. And that's true for all z. Moreover, that enumeration of E can be computed in polynomial time. Unfortunately, not as fast as the previous guys, but with work at most c n squared log n and storage at most c times n. The storage is optimal, of course. There are n data points, so the storage had better be at least n. The work, I don't know whether the algorithm that claimed in the slide is optimal or not. I have no idea. Maybe one can do better. Okay, now at this point, I could spout other theorems or other algorithms or give some ideas behind the algorithms. I personally enjoy talks that give some idea of the proof without getting bogged down in too many details, as opposed to a laundry list of many theorems. So I'm going to give you some of the ideas behind some of the algorithms. So we're going to restrict attention again to Cm of Rn. Sobolev spaces are simply harder. I won't talk about them further. And what I'll do is introduce enough notation and definitions to explain the ideas. Then I'm going to state a main theorem and say a little bit about how to use the main theorem to produce the algorithms. Okay, so let's fix the notation. Well, let's fix little m and little n, and our Banach space X is Cm of Rn. Okay, for a nice function, capital F, J sub x of f, the jet of f at x, is the mth degree Taylor polynomial of f at x. And here I've written down the mth degree Taylor polynomial at x. That polynomial is an element of the vector space script p consisting of all such. So script p is the vector space of all mth degree polynomials on Rn. And so the jet at x of f is in the vector space script p. Okay, that's the notation. Okay, in that notation, I would like to state Taylor's theorem. So here it is. We have a Cm function. We have 2 points x and y. Let's say they're not equal to avoid trivia. And then, of course, if x is close to y, the Taylor polynomial of f at x is very close to the Taylor polynomial of f at y. And here is the estimate that expresses that precisely. And again, it's just Taylor's theorem. Okay, so we'll be using that. Okay. All right, so now let's fix an interpolation problem. So we fix a finite set E in Euclidean space. We fix a function, little f, defined on E, real valued. And what we want to do is to find a function capital F in our Banach space Cm of Rn with the property that capital F agrees with little f on E, but its Cm norm is at most capital M. And we would like to do this with capital M as small as possible. Okay. So that's what the interpolation problem is. Okay, well, in order to answer that, we ask ourselves a key question. So let's fix a particular positive number, capital M, and let's suppose that there exists a capital F in Cm that agrees with the data, capital F equals little f on E, and yet the Cm norm is less than capital M. Of course, if we're greedy and capital M is too small, there may not exist such a capital F. The key question that I want to ask is, if there is such a capital F, what can we say about its Taylor polynomial at a given point? This given point might be anywhere, but for purposes of the talk, either it will be near E or actually very soon it will be in E. Okay, so in order to formulate the question more precisely, I'm going to define this set gamma. So given an interpolation problem, little f and capital E, as usual, and given a positive number, capital M, I'm going to let gamma, or gamma sub f of xm, or maybe just gamma of xm, that's going to be the set of all jets, or all Taylor polynomials at x, at the given point, of functions capital F that agree with the data and have Cm norm less than or equal to m. Okay, so that sits inside script P. It's a set of mth degree polynomials. Notice that it's possibly empty because if I demand, if I'm greedy and I take m to be small enough, there will be no such capital F, and so the gamma will be empty. But if capital M is not too small, then gamma F will be non-empty. Okay, And if it's not empty, then notice immediately a first property of the gamma, it is convex. Obviously, if you take, if I take two functions, capital F sub 1 and capital F sub 2, if they both agree with little f on E, and if they both have CM norm at most capital M, then I can take, 2/3 of one plus 1/3 of the other, and that will again be an interpolant, and it will again give an entry into an element of the gamma. So the gamma is a possibly empty convex subset of script P. And the problem that I want to pose is to compute the approximate size and shape of that convex set. That's, of course, a vague statement, and I'll make it more precise in a minute. But notice that the gamma contains a tremendous amount of useful information. For example, is there an interpolant of norm at most M? That's equivalent to asking whether the convex set gamma is empty. And so already, if we simply ask whether the convex set is empty or non-empty, if we can answer that, then we can find the trace norm of little f. We can find the least possible or the inf of the norms of interpolants. And if we know not merely whether the gamma is empty, but we know its approximate size and shape, we have a powerful hold on what an interpolant can look like. All right, so what does it really mean to compute the approximate size and shape of the convex set gamma? And what it means is that I would like to be able to compute convex sets that I call here gamma approx with the property that shown on the slide. So I don't precisely fix the value of M, but if I want to understand the actual gamma, the true gamma for a given M, it is contained in the gamma approx if I make that M somewhat bigger, and on the other hand, it contains the gamma approx if I make M somewhat smaller. And these C and C are supposed to be controlled constants, which means in this setting that they depend only on little m and little n in the specification of the Banach space Cm of Rn. Okay, so that's what we want to do, and if we can do that, we're in very good shape. Okay, so what I'm going to do is explain how to compute gamma approx that works, and then say a little bit about how to use those gammas to produce the algorithms promised. All right, so how do we compute gamma approx? Well, by induction on an index L, we're going to define possibly empty convex sets gamma L in the vector space of all nth degree polynomials, okay? And the gamma L will satisfy three key properties, okay? By the end of the talk, the first two will be completely obvious to you, and the third, unless you've thought about the subject, will, I think, not be completely obvious. Okay, so the gamma L have three key properties. First of all, they're compared to the gamma that we actually want, they're too big. So gamma L of xm is always going to contain the gamma that we really want, gamma f of xm. That's the first basic property. On the other hand, the role of the index L is that every time we increase L, the gamma gets smaller. So each gamma is too big, but each gamma is gamma L is too big, but as L gets bigger, the gamma L's get smaller. And so with luck, after a while, they won't be much too big. And the third statement is that if you carry this procedure out L star steps, where L star is a large enough integer constant depending only on little m and little n, remember those are the parameters of our Banach space, then although gamma L star contains the gamma that we want, it is nevertheless contained in the gamma that we want if we increase m by a constant factor. And so that means that by the end of the game, when we take L equal to L star, we will have found a gamma approx that does the trick. So I would like to explain in the next few slides how to construct gamma L that do the first two things that I described, and then at the end there will be a theorem that gamma L star will do the third thing. That's the plan. Okay, so let's define the gamma L by induction on L. So let's start with the base case L equals 0. And so look at the slide. gamma 0 of xm is simply the set of all polynomials with the property that their value at the given x is equal to the value of the data, little f, at x. So the function agrees, the value of the function agrees with the data. And furthermore, the polynomial and all its derivatives up to order m at the point x are at most capital M. Now, certainly, all right, that set is obviously convex. Notice that it's empty because if m is smaller than the absolute value of f of x, then you can't do that. Okay. So it's possibly empty, but it's convex. Obviously, it's defined by linear constraints. And notice that it controls, I'm sorry, gamma 0 contains gamma f of xm. Gamma 0 of xm represents what you can say about the jet of an interpolant by looking only at the point x and at no other points. Here and below, x is going to be a point of E. We could ask what the gammas look like at other points, but we won't have to. So from now on, x is always a point of E. Okay, so I hope it's simply obvious that gamma 0 of xm contains gamma f of xm, and so we have taken care of the base case, L equals 0. So now I'd like to explain the induction step. So let's fix an L, and let's fix a capital M, and let's suppose that we have defined possibly empty convex sets gamma L of xm sitting inside script P with the property that they all contain gamma f of xm. Okay. The induction step is, given that, we will define possibly empty convex sets gamma L plus 1 of xm with the property that they are contained in the gamma L, but they contain the gamma f. And if we can do that, that will complete the induction step, and that will establish the first two key properties that I promised you of the gammas. Okay, so what I've got to do is to define gamma L plus 1 that does this, and that'll happen on the next slide. So here it is, gamma L plus 1 of xm. Okay, for a given point x in E, gamma L plus 1 of xm consists of all p in gamma L of xm with the following property. So look in the box. Given a y in E other than x, there exists a p prime in gamma L of ym that satisfies the estimate that you see on the slide. Okay. Now, that's the definition of gamma L plus 1. Now, clearly, gamma L contains gamma L plus 1. Why? Gamma L plus 1, by definition, consists of all p in gamma L such that something or other happens. So, of course, gamma L contains gamma L plus 1. Thank you very much. It takes just a little bit more thought to understand why gamma L plus 1 continues to contain gamma f by Taylor's theorem. And so we'll see on the next slide the details written out. So suppose that P belongs to gamma F. I've got to show that it belongs to gamma L plus 1. Well, if P belongs to gamma F, then by definition, there is an interpolant. There is a capital F in Cm that agrees with little f on E and has Cm norm at most capital M and has jet P at X, right? P belongs to gamma F of xm, and by definition, that means that P is the jet of a suitable interpolant. So we've got this function capital F floating around. Now, if y is any point of E other than x, we can simply set P prime equal to the jet of that interpolant F at y for the same F. And so then P prime belongs to gamma F of ym because it is the jet at y of a suitable interpolant. And we've assumed by induction hypothesis that gamma f of ym is contained in gamma L of ym. So P prime is in gamma L. Yes. And the estimate, the desired estimate for, here I hope you can see my cursor, the desired estimate for P prime minus P is obtained by just noting that P prime is the jet of F at Y and P is the jet of F at X by definition. And this is less than or equal to this guy. That's Taylor's theorem. And the norm of F in Cm is at most capital M. And so that's here. And so this guy is less than or equal to that guy. And that is precisely, if I can go back to the previous slide, that's precisely what we needed in order to show the defining property that P should belong to the gamma L plus 1. And so that's the proof that gamma L plus 1 contains gamma F. So it's really just Taylor's theorem, and so our induction is complete. So now we've defined the gamma L for L greater than or equal to 0, X in E, and M positive. And so we've got very easily two of the three basic properties of the gammas. But now the third basic property is not so easy. It's a serious theorem. And the theorem is, again, that for L star, a large enough integer constant depending only on little m and little n, the parameters of our Banach space, we have that the gamma L star of xm is contained in, not contained, but is contained in the gamma f of x with parameter c times m. And so that means that we have the inclusions here on the slide. And so we have succeeded in computing the approximate shape, size and shape of gamma f. We can use these guys as our gamma approx. Okay, so we've succeeded in computing the approximate size and shape of the gammas, and now we're going to use that main theorem in order to produce algorithms. And this is going to be a very, very superficial summary. So first of all, to compute the triple norm, I seem to have made a systematic typo. There should be x of e instead of x throughout. But in order to compute the triple norm, I simply want to, well, all right, wait. There are two things we want to do, I should say. We want to compute this triple norm, and we want to compute an interpolant with the m as small as possible. Okay, to compute the triple norm, we simply look for the smallest m for which the gamma is not 0. Again, it's an inf, not a minimum, but we look for that, and that's the triple norm. And that can be computed because we can compute the gamma L star. Everything I said so far was constructive, and that's in principle how we compute the triple norm. Now, to compute capital F, what we do is we don't just apply the main theorem, we look inside its proof and we implement the proof. The proof is constructive and it produces a capital F. That's all I have time for, and maybe that's all you have patience for. In principle, that's how to do the calculation of the trace order of magnitude of the trace norm and the interpolant. However, that computation would require a huge memory and running time. It's not what we actually do. And so to obtain an efficient computation, we modify the inductive definition of the gamma L to make it easier to compute them. And we bring in ideas from computational geometry. Explaining how to do that is a long story. Let's declare victory and not go into detail. We've seen some of the ideas behind the algorithms that solve interpolation problems, but I haven't said anything about how to deal with outliers. But fortunately, the main theorem and the gammas let us do that too. And again, let's simply declare victory. Now, I've given this lecture I'm close to the end without giving due credit to anybody. That's not so cool. I have simply here a list. As I looked at my list, I'm appalled. It's incomplete. So I will try to remedy that. But the ideas, well, the math behind the algorithms goes back ultimately to several papers of Hassler-Whitney in 1934, to the two Israeli, previously Soviet mathematicians, Yuri Brudny and Pavel Schwarzman, to a French mathematician of the 1950s, whose name I unpardonably forgot to write down, Georges Glaeser, Glaeser. then to Canadian mathematicians Ed Bierstone and Pierre Millman, and the Polish mathematician Wiesław Pawłowski. I hope I'm not mispronouncing his name too badly. To the Israeli mathematician Boaz Klartag, and to to my former students and dear friends Aryeh Israel and Garving Kevin Luley. Those are the mathematicians, and I mentioned ideas from computational geometry, so I want to mention computer scientists Callahan and Kosaraju, and Arya, Mount, Netanyahu, Silverman, and Wu. Regarding those last collaborators, I think that Netanyahu is related to Bibi. I'm not quite sure what the relationship is, and I forget which one of them was actually a computer science prof at the University of Maryland.
David Mount.
Aha, thank you. Okay, and is he still?
Yes, he is. Yes.
Okay, okay. All right. Now there's a lot that I've omitted, so I want to mention a little bit. Let's see, what time is it? How am I doing? Oh, I've okay. Oh dear. I'm sorry I've gone over. Let me just say that of the I mean there are many additional problems. It would be very natural, for example, to look at functions with subject to constraints. For example, maybe our interpolant has to be positive, or maybe of absolute value less than one, or something like that. The one of the main experts on that, I would say the main, well, yes, one of the main experts on that is in the audience. That's Black, and the best relevant theorem on that problem is due to him. So there are further problems. I've gone over time. I'm sorry. Let's stop.